Gave you a note sheet the other day. It has a chi-squared. One side was goodness of fit, and then down below it was test of independence. We're going to focus on the independence today. So now, people that are chatters, you need to be quiet, okay, because we're going through this. There's some big things coming into this that will pop up, and I'm afraid you're going to miss it. What I'm going to do is I'm going to walk through the notes again like I normally do. Okay, they're just the generic notes where people kind of go, okay, I see where we're going. I don't exactly understand how to do the expected or whatever the scenario is. And then what we're going to do is we're going to walk through an example. And by walking through an example, I think you probably agree over the last couple lessons that that's probably the easiest way. Walk through an example, you go, oh, I see what's happening. So we'll walk through an example, and that'll probably make a big difference. Okay? All right, first thing I'm going to define is homogeneity. Okay? Web definitions. It says the quality of being similar or comparable in kind or nature. There's a remarkable homogeneity between the two companies. In other words, the two companies seem to be about the same. So when we do a test of homogeneity, we're testing to see if the companies are about the same. Or is there a difference between them? Okay? Just don't have to write this down. This will come up. I just wanted to define this. Test of independence. Chi-squared. There's two tests of chi-squared. There's the chi-squared goodness of fit, and there's the chi-squared test of independence. If you do a chi-squared test of independence, there are two different types. One is association, and one is homogeneity. Okay? One's homogeneity, and one is association or independence, however you want to look at it. Now here's what happens. Is they used to just teach us as test of independence. Now all of a sudden our book splits it up into two different types. We're not going to focus too heavily on the two separate parts. If you get stuck, it even says this right in the book. If you get stuck and you're not exactly sure which one, just say chi-squared test of independence. Okay? Either way, a test of independence has got to be bigger than a 1 by something. Okay? And we'll get to that. Here's your generic phrase. H null, there is no relationship between row and column, or they are independent, right? If they're independent, then there's no relationship or association between them. The alternative, there is a relationship between them. In other words, they're not independent. For example, without even looking at the sideboard, do you think there's a relationship between your gender and people's eye color? No. Males have more green than blue. Females have more blue than hazel. Probably not. So do you think they're independent? What one person has versus another person, male or female, I'd say it probably doesn't matter whether you're male or female as to what your eye color is, right? That's what you're testing. H null, there is no relationship between gender and eye color. That's what we're going to test here coming up. There is a relationship between gender and eye color, would be our alternative. That's what we are going to try and test. H null for test of homogeneity. There is no difference between row and column. There is a difference between row and column. Key here is that you're dealing with 2 or more independent random samples. That's going to be the best way to determine the 2. Whereas test of independence, there is an association between row and column, or they are independent, or they're not independent. There is an association between row and column, so in other words, there's something else going on. That one is a single random sample. Both of them are dealing with categorical variables. Right? All that data that you see on the sideboard, quarters of the year, handedness, eye color, gender, that's all categorical data that we did tallies in. But we're dealing with categorical information. This slide you have on the back side of the notes that I gave you. I just literally copy and pasted it in. Let's go back to the generic notes. Chi-square test of homogeneity or association, or just chi-square test of independence, is got to be bigger than a 1 by something. This part is important. Greater than a 1 by something. If you're dealing with a 2 by something or bigger, then you're dealing with a test of independence. For example, eye color is a 2 by 4, right? Male, female, and then the 4 colors. So that's a 2 by 4. What happens is this is generic. This opens it up to anything. So now I might have 50 stores at Walmart, 50 Walmart stores, and I might have every month of the year, Well, can you imagine doing a chi-square test for a 50 by 12 matrix? It's a lot of work. So obviously calculators and your computers would help out. Minitab would be what they're probably using. But we're unlimited now. I can make that as much data as I want, as big as I want. We're not limited anymore. And that's why chi-squared tends to get used a lot. H and O, there is no association between row and column, or they're independent. There is an association between row and column, or they're not independent. That's the generic. Here's your equation. Has your equation changed from the chi-squared goodness of fit? Has that equation changed at all? No. Here is what has changed, is your expected count. In number 17 from last night, where they talked about smooth peas versus wrinkled peas, and they gave you, it was a ratio of 3 to 1. 3 were smooth and 1 was wrinkled, so you put them into fractions, and then you do 0.75 times your total count. That's where people will make mistakes. They'll do 3/4 times 423 and 1/4 times 133. It's 3/4 of the total is what we would expect. 1/4 of the total is what we would expect. That's where people make mistakes. So hopefully you'll catch yourself on that. But in this case, I can't do this anymore because it's not a 1 by something. It's a 2 by something. So how do we find the expected? You got to take your row total times your column total and divide by the total of everything that you got. And I'll show you an example of that. And then you have to do that for every single one of those cells. So I would have to do it for 8 cells if I'm doing gender and eye color. It's a lot of work, but I'm going to show you a shortcut. Your degrees of freedom has changed. Now all of a sudden it's row minus 1 times column minus 1. Very different than what we're used to. Your assumptions have not changed. Simple random sample, expected cells greater than 5 or no more than 20% of them can be less than 5. None of them can be less than 1. And then after you find your chi-squared value, you can look it up in the table, but your calculator will give you a specific value as well. So out of that whole page, what is really that new? It's this. Your null and alternative is worded a little bit differently for a chi-squared of independence, test of independence. Your degrees of freedom and your expected count. Those are the things that are pretty new. Otherwise, everything else is about the same as we've been working with. Then at the end, if you do find that there's a difference, just like always, try and pull out those cells that you go, I think there's a difference between here and here. And those are the ones that you're going to want to walk through. Chi-squared on your calculator. I gave you directions on how to do it on your calculator. Something I would maybe add, and that's this part in red here. So you're going to plug your data into matrix A. Then you're going to do a chi-square test. You're actually going to do the test, and it automatically puts your expected cells into matrix B for you. Then to write out your expected cells, do edit matrix B to find your expected cells, because you have to write those out. No way around it. They are actually looking for the box where you've written out your expected cells.
Can you not do that on an 83?
Everybody can do this. This chi-square test of independence, everybody can do. It's just called a chi-square test ... is what it is. Everybody with me? The only thing I would add to this is that edit matrix B to get your expected values, because it fills it in automatically for you. And then I had this little note, which you already know. TI-84 has a chi-square GOF test, but we've already gone through that. All right, let's walk through an example. H null. You told me earlier that you think gender and eye color are independent. So then our research hypothesis would be, I think gender and eye color are not independent. That there's something going on, gender and who might have more of what color or something like that, right? So we got to go through and prove it. This data right here is our observed. I just copied it off the table on the sideboard, right? We had 24 males with brown eyes, 6 with green eyes, 25 with blue eyes, and 6 with hazel. For females, we observed that we had brown 15, green 13, blue 13, and hazel 1. And then I just did the totals. This is 61. This has a total of 39. You could go through and do that for every row and column. You can see over there that I've done that. This is a row total of 42. This was 19. This was 38. And this was 7. For a grand total of 103. So 103 people participated in my study over there. Okay, let's walk through this. H null, gender and eye color are independent. The alternative, gender and eye color are not independent. Matt, if I get in your way, feel free to scoot. First thing I'm going to do is chi-square test. What kind of test is this? Independence or homogeneity? Anybody know? Oh, Nick, so quick. How did you know?
Testing if they're independent.
Okay, in the wording itself, you're very right. But how come I didn't say gender and eye color are different? How many samples do we have? One. Everybody in my sample, you just came in and you put your little data in. Remember, if we go back to this is one of the key things here. 2 or more. Oops, I just crossed it out. 2 or more, and that's homogeneity. Whereas if you have a single, it's a test of independence. And this was a single. I just asked my students. I didn't then go and ask another classroom downstairs or something like that, another teacher to find some data. This was only one sample. Okay? So this would be a chi-squared test of independence. So we name it. What comes next? We just go right down the state plan, do conclude, or high-TAPC. HY in the test, the assumptions. Simple random sample, let's assume we're good there. Independence, there was no replacement, so I have to test. Independence, let's check. 10 times 103 is 1,030. Is that less than the population of RHS students? Yeah, so we're okay there. So independence is good to go. Then I have to test my expected cells. Assume that this is not filled in yet, okay? Are all expected cells greater than 5? You have to absolutely put together an expected cell chart, okay? Assume that these numbers are blank, because I haven't shown you how to do that yet. So you write this chart out, and we got to fill that in. Remember how to find your expected. So if I want to find the expected for, let's find the expected for that cell right there. Male brown eyes. By finding the expected cell, remember it's row times column total divided by the total of everybody. What's the row total for that cell? What do we get? 61. Row total right here. If I follow this across, there's my row total. So 61. Column total for that cell was 39. Divided by the total of everything, which is 103. This number right here goes to the bottom. Somebody want to do that for me?
23.1.
That, oh, I already got it. There's your 23.1. Now I'm going to show you a shortcut here of how to find it very easily. Otherwise, you'd have to do that 8 different times, right? Because there's 8 different cells here. 1, 2, 3, 4, 5, 6, 7, 8. What if this was a 50 by 12 matrix? That's a lot of work trying to find those expected cells. So your computer software, your calculator will do it for you. However, what will happen is they could pop this question up and they'll say, hey, here's the scenario, here's the data. What's the expected count for females with blue eyes? And you didn't have to do a test. It was a multiple choice type of question. And they just threw that exact cell out. So you're sitting there going, well, expected for females blue for this cell right here. So now I'd have to look at a different female blue, right? So let's go back and fill that number in. Would be row total, which is 42, times column total, which is going to be 38, divided by the total of 103. 42, 38, 103. And you do that, and it should give you 15.5. Now, you're not going to have to do those 8 different times. I'm going to show you the shortcut. Take out your calculators. Follow along. If you're falling asleep, follow along. This is a good way for you to kind of wake back up. You're going to have to know how to do this. Otherwise, you're really in for a lot of work. If you need it, anybody need to grab one of mine? You're going to want to follow along with me, so if you don't have your own. Everybody can do this, whether you have an 83 or an 84. Okay, first thing we're going to do is go to second matrix, which is over the x to the -1. And then there might be some listed out there that might not in terms of what's in here. Okay, go over to edit. Let's edit 1, or A. And it gives you a little cursor. You can see it right here. What's our matrix for this scenario? What size? It's 2 by 4. Right? So hit 2, enter, moves you to the next one, 4, enter, and notice all of a sudden it moves you down and they give us a 2 by 4 matrix that we can fill in. Put the observed date in there. What do we got? 24, 6, 0. 24, 6, oh, it should be 25, sorry. 25.
Oh gosh, there you go back.
Click over.
And 6. Hit enter, just keep hitting enter. And then 15. 13, I'm just grabbing them off the sideboard there, in case you're wondering. 13 and 1. Or you can grab them off of these numbers right here. So all it's done is I've taken this data and put it into my matrix. You with me?
Yeah.
Anybody having trouble with that? All right, that's probably the hardest part, because now watch. We actually have to do a chi-square test. Before I do the expected cells, let's actually do the test, because then it helps. Stat, test, chi-squared test, ... not the GOF one. Hit enter. Notice this is how you can remember. Oh, that's right, this one works with matrices, because they give you. Observe, did we put matrix A? Where do we want them to put the expected cells for us? In B. It'll put it automatically in there for us. All right? All you have to do is go down and hit calculate. There it is. There's your chi-squared value, there's your p-value, there's your degrees of freedom. Let's see where those numbers came from. Let me go back to this. And what I would do is I would write that down. Chi-squared was 8.81.
Yep.
P-value was 0.03.
19.
So 0.032. What about our degrees of freedom? Row minus 1, which is, there were 2 rows, right? Male and female. Times column minus 1, there are brown, green, blue, or hazel eyes, so 4 minus 1 gives us 1 times 3, or 3. That's how they got the degrees of freedom. Now, they will, so you don't necessarily have to find it, you do have to list them out though. So far, I've got these numbers. I'm just writing them down because eventually I'm going to need them anyways. Now, go back to your calculator. Let's go back and go to second matrix. Let's look at, notice all of a sudden you'll have a 2 by 4 in spot number 2 in matrix B. Go over and hit edit. Matrix B, so number 2. There's your expected cells. They've done the row total times column total divided by total. They've done this whole thing right here for us. So you don't have to. It's weird though, because you got to put your data in observed matrix, then do the chi-squared, then go back to the matrix B and edit it to find what those numbers are. But they do it for you, so it saves you a lot of time. I mean, this would be a pain, right? So then that's where all of these numbers came from. This cell, this printout right here, has to be there. You have to have that. They have to be able to see it somewhere. If they do not see an expected cell, then they're going to say, well, then how did you test if they're greater than 5? Therefore, I don't know if I trust your data here. I don't know if I trust your conclusion. Nothing else I can conclude. That's why they can dock you a lot of points for that. You've got to have that written out, and they push that a ton. I don't know how you do it otherwise. Okay, so let's go make our conclusion. Are all of our expected cells greater than 5? No. Look at, I've got 2 of them. However, that might be okay. How many am I allowed? Expected cells should be greater than 5, or no more than 20%. In this case, I have 2 out of the 8 cells, which is what percent? A fourth, right? 25%? Oh. Ouch. So, 2 cells less than 5, so proceed with caution is what I would put in this case. Now, would they give you a question like that? Caution. On a test where you have to proceed with caution, not without setting you up. But because I'm using actual data, I run into issues like this. So, yeah, at the end, I would question whether my data is correct or not. Everybody good with this part? So we went through the assumptions. So all of that just was to help us get through the assumptions. But now the rest of it's easy. You just finish the hard part. Then we got to set it up. Remember, we got to find the p-value. So chi-squared is equal to observed. So 24 minus expected of 23.1 squared divided by the expected of 23.1 plus, I'm just going to go to the next cell, 6 minus 11.3 squared over 11.3. Don't forget to square it. Plus dot, dot, dot. You don't have to keep writing them out. Just do 2 of them so we go, yep, they set it up right, and then move on. It's just like the binomial distribution, remember? I said do 2 of them and then you can be done. Just do dot, 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 same kind of scenario. We've got our degrees of freedom. We wrote that down when we were looking for our expected cells. We got our chi-squared value and we got our p-value. Everybody with me? So far, H null alternative is a little different, the way we word it, just in terms of independence or not. Name it, not a big deal. Assumptions, not a big deal. It's just how to find the expected cells. That is new. That is something that's probably one of the biggest things out of this test, and how to find the expected cells, both on your calculator and by hand. Otherwise, setting it up is the same as goodness of fit. Degrees of freedom has changed a little bit, but your calculator will give it to you if you want. You don't have to show the work, but you will have to list that out. Chi-squared value, your p-value. Then you got your conclusion. So what would your conclusion be? At alpha 0.05, let's say. So what would we do? Fail to reject or reject the null? At alpha 0.05, we reject the null. In favor of what? Okay, be even more specific. Context of the problem.
There's a relationship between eye color and gender.
Look what we just figured out. I didn't have anything to do with this. You guys put your data on there. We found that there's a relationship between, or some kind of association, or that eye color and gender are not independent. Okay? At alpha 0.05, we will reject the null in favor of gender and eye color or not being independent. However, our assumptions of expected cells greater than 5 was not met. So remember, we got to proceed with caution. Just keep that in mind. Am I done then? Very good, Cal. List things that might be what's throwing us off. If you find that there's no evidence that you're going to stay with the null, then you're done. If you rejected the null, well then why did you reject the null? You have to put that little sentence in there. Let's go back. It's kind of scribbled all over the place. But see if you, here's your observed, here's your expected. Which cells do you think are possibly throwing this off? See if I can pick a different color here. I'm going to use smiley faces. Which cells? How about 24 and 23.1? That's good. 6 and 11.3? Is that a big difference? Maybe. Let's come back. 25 and 22.5? No. 6 and 4.1? No. 15 and 15.9? No. 13 and 7.8? Maybe. So you're saying maybe this one right here. How about 13 and 15.5? No. 1 and 2.9? No. I would say this one is also 1. 6 versus the 11.3 is almost double. So I would come back and say I would reject the null in favor of that they are not independent, that perhaps there's a difference between male and female and green eye color. They were off from our data and what we would expect. That's all you would have to say. You don't have to explain any more than that as to why that might be. You don't have to explain that part. The green eye color for male and female seem to be different. Oh, we came off. The green eye color for male and female seem to be different. Now, here's what happens. Why do people do a chi-squared? Let's say you do have 50 stores by 12 stores, by 12 months, all right? And you go through this huge chi-squared and 2 stores pop out. And you go, wait a minute, how come sales for those 2 stores are way low? What is going on with those 2 stores that their sales are low? So then all of a sudden you'll pull out that information and you'll do a proportion test or a t-test or something specifically for that store. It's usually a proportion test. And then you'll do one for the other store. So instead of doing 50 by 12, or what are we talking, 600, instead of doing 600 proportion tests, you're doing a chi-square test, pulling out the 2 or whatever you've got that are making a difference. Now you only have 2 proportion tests. So it saves you a lot of time. That's why we do a chi-squared. An example of something like that would be down here on Highway 3. If you go down towards 52, I think it's over by where you take a right to go to Inver Hills Community College. Right there on the left, there's a brand new store. What brand new store just opened up there? They just cleared it out and it was empty for a long time. And now all of a sudden they put a store in there. Anybody know what it is? Right down on Highway 3. If you take 3 all the way north.
Target?
Yeah. They just put a brand new Target in. Now, is there anything else there at this point? No, there's a strip mall, correct? Didn't they? I think they put a strip mall in that's probably empty right now.
Yeah.
But what happens is they wanted a core building, and Target came in. Now, does Target get something out of this? In a lot of cases, yes. What will happen is the city says, we need some big company to come in. And then they'll say, Target, if you come in, we'll give you 10 years free of taxes. You don't have to pay taxes for 10 years. Target goes, okay. That's pretty huge. All right, fine. We'll open up a store there. That'll be our benefit. Because once they open up, the city might go, yeah, but we're losing all that tax money. That's a lot of money. But what happens to that strip mall as soon as a Target opens up, especially a Target? A lot of shops are going to go in there. I can bet you there's probably going to be a massage place, a nail place, a hair cutter, probably Great Clips or something like that, or a sports clip. You're going to get a little bakery in there. All of a sudden, all these other little things are going to start to pop up. The city gets tax money from them. But even more importantly, What is happening directly north of that store? Anybody know? It's going to explode here if it hasn't already. There was nothing there except, I don't know, trees and maybe farmland or something. And all of a sudden there's a bunch of homes going in. Think how much tax money they're getting. Let's say 100 homes go in there, plus that strip mall fills in. Do they care that they're not getting the money from Target? That's all extra tax money. Because a Target opened up, boom, the rest of this opened up. So when Target goes to look at their sales, they're going to say, look, sales of this store is really high. Why is the one in Inver Grove so high? Oh, that's because we're not paying taxes. That'll change once the 10 years is up. So then they put that one aside. Ooh, hey, that's to our benefit to do that. Or taxes, their sales are really low. Why are they really low? Because they're the only store. Once that starts to fill in, then their sales will skyrocket. Because now people will start going in. Are they going to go to that Target if there's nothing else around? Probably not. They'll probably go to the Apple Valley Target where you've got everything you might possibly want there, right, at this point. Questions on that? All right. You will also get a Minitab printout. You may see something similar to this, where they've gone through and done the chi-square test for you. They've done it on the printout. They're just saying, do you understand this? And they've told us that we should prep our students for some kind of printout, Minitab or SPSS. They're all kind of about the same. This is expected counts for chi-squared. This is 1, 2, and 3. I don't remember what they stand for. None, French, Italian. I don't remember what it is. But either way, what you've got here, when you get a printout like this is your observed data. This right here is your expected data. This right here is your chi-squared value for that cell in itself. When you go back to this cell in itself is a chi-squared value if you did it on your calculator. That's what this number is for all 9 cells. Here's your chi-squared value total. Here's your degrees of freedom. Here's your p-value. Thank you very much. I don't have to do any work. It's all done for me. But here's what they'll do, is they'll give you a scenario. What would you do? They give you this picture and they'll say, here's the data, make a conclusion. At alpha 0.05, what would you do? Reject the null in favor of there being some kind of association between row and column, whatever those two things are, right? But if we rejected the null, you got to go back and talk specifically about any changes. Do you see any cells that might be causing a little stir?
2 French and 2 Italian.
Yeah. I would say this one and this one are the ones that are causing. Look at everything else, they're not that far off. Maybe this French one, but it's really going to be French and Italian too. So then what happens is you'd pull out those 2 cells and do like a proportion test or something to look at the data. Saves us a lot of time as opposed to looking at all 9. Or you find that that they are independent, then you don't have to do any extra work. Then you're done.